Okay, good morning. So this is our third lecture, and in the previous lecture we have started our discussion on heat engine, refrigerator, and heat pump. We will continue that, and majorly that discussion will also lead to recapitulation of some concepts of your thermodynamics. Okay. So while talking about heat engine, if you recall from the concepts of thermodynamics, particularly from the second law of thermodynamics, we have studied some system like this where we have a source of heat at temperature T1. From this source we extract Q1 amount of heat, and then we have some arrangement inside this circle which is particularly called as heat engine, and this heat engine gives us W net amount of work output. And in this process, because we have to operate this heat engine in a cyclic manner, in order to operate it in a cyclic manner, it also rejects Q2 amount of heat. Okay, and this Q2 amount of heat in general it can reject at any temperature T2. However, if I say that I am operating with perfectly reversible heat engine, then this T2 has to be nothing but equal to the ambient temperature, the atmospheric T3. So let me over here put a fixed line which will be actually representing my temperature TA. Now the two terms I will be using over here. One term I will be calling as internally reversible process. Other term I will be saying as totally reversible process. So do you have idea about this or shall I explain it? Because this will be required. So shall I explain it? Okay. For example, let us understand this with the help of a very simple example. Say I have a pan. Okay. And in this pan I am having water at 25 degrees Celsius. Okay. You have placed this on an electric heater. So you can see nowadays we have these electric induction heaters where we can actually maintain the temperature of this electric heater at some constant condition, or even we are having some hot plates also. Okay. So say I have this maintained at some 60 degrees Celsius. Now, what will be happening? This is at 60 degrees Celsius. The pan which is placed over this contains water at 25 degrees Celsius, and of course, pan initially will also be at 25 degrees Celsius. Now, when the heat, so in this case, my system is only water. Okay, so I am not bothered about the other things. My only concern is water. Okay, so when I will start heating this water, what will be happening? You will be finding that the bottommost layer of the water will first immediately start heating. Okay, so in this bottommost layer, I will be finding temperature will be greater than 25 degrees Celsius. Okay, however, far away from this, okay, to the other end, of course, temperature is close to 25 degrees Celsius only because it is significantly high. Okay. Now, once you started the heating process within the water itself, in the bottom layer of water you have some other temperature, in the top layer you have some other temperature. So, because of temperature difference, of course, internally also there will be some transfer of heat. Now if you see, this heat is transferring from bottom layer of water to top layer of water, and when this heat transfer is taking place between these two layers, there is finite temperature difference. Is this point clear? There is finite temperature difference. Whenever there is finite temperature difference, it means that process is not reversible. Okay, because for a reversible heat transfer process, the temperature difference between two portions which are exchanging heat has to be infinitely small. Okay, for example, if I say that I have water top layer is 25 and bottom layer is 25.009 degrees Celsius. 29.00999 something degrees Celsius. So here also what I am having? I am having temperature difference, but this temperature difference is dT, which is called as infinitely small temperature difference. And this type of temperature difference, where say this temperature is say 35 degrees Celsius and top temperature is 25 degrees Celsius. So difference is how much? 10 degrees Celsius. 10 degrees is a finite number. So this is my delta. So when I am having finite temperature difference between the two portions, then the heat transfer process cannot be reversible. Heat will be only transferring from 35 to 25. It cannot transfer from 25 to 35. It means process is not reversible. But if I say that my one temperature is 25.0099, other is 25, I can have heat transfer in both the directions because of infinitely small temperature difference. So that's why this second process is actually what type of process? Reversible process. Okay, but the first process is not at all reversible. Now after this there are two terminologies. One is internal reversibility, other is external reversibility. Internal reversibility means if water is my system, I will check temperature difference only within the water. If only within the water temperature difference is infinitely small, it means process is internally reversible. Okay, let me give that example also. Now let's consider you have the same water pan, but here water is in the saturated state. What is the meaning of saturated state? You will be having some portion of liquid water. At 1 atmospheric pressure, its temperature will be 100 degree Celsius. Along with this, you will be having some vapor also, and this vapor will also be having temperature 100 degree Celsius. Now, if you consider this as part of your system, and if you provide heat from a source which is at say 110 degrees Celsius. Now what will happen? When you will be adding heat, will there be any change in temperature of water? No. But what will happening because of this heat transfer, some amount of water from liquid state will change to vapor state, but its temperature will always remain same. Okay. So once within this entire portion, in this scenario, in the entire portion of the system, wherever you go, everywhere your temperature is what? 100 degrees Celsius. But system is also receiving some amount of heat. So it means this heat addition process is taking place at infinitely small temperature difference between the systems. So it means this heat addition process is internally reversible. Is this one clear? But if you see external to the system, so of course this heat the system is receiving from some source which is at temperature 110 degrees Celsius. So when you have 110 degree and 100 degrees Celsius, now this temperature difference with external system is finite. So it means this heat addition process is externally irreversible. This is externally irreversible. Okay. And I can have another scenario where my liquid is at 100. I have some water vapor also. And whatever my source is there, it is at temperature of 100.0999 degree Celsius. In this scenario, what will happen? Again, I will be having some addition of heat. Okay. Because there is infinitely small temperature difference between the external surface. So now within system also we have internal reversibility, outside system also we have external reversibility. So this is external reversible process. If any process is both internally and externally reversible, it is called as completely reversible process or simply the reversible process. Is this point clear? So this type of terminology is very important to understand, because whenever we will be talking about different type of heat engine and heat pump or refrigerator cycles, we will be finding that we will say some cycles which are totally reversible. So totally reversible cycles are not practical, but these acts as benchmark. Whereas internally reversible cycles are idealization of the practical cycles, which are basically possible cycles. Okay. So one important difference also you have to note over here, why we will be later on finding that the total reversible cycles are practically impossible. One of the reason will be from this understanding only. If you have finite amount of temperature difference, then we know that rate of heat transfer is always directly proportional to temperature difference. Okay, so it means that when you have finite amount of temperature difference, then the rate of heat transfer will be significant and process will be taking lesser time. But if you have infinitely small temperature difference, then for the same amount of rate of heat transfer, you have to actually do the process for infinitely long duration. Is this point clear? All are clear with this idea? So it means totally reversible heat addition or heat rejection process is nothing but infinitely slow process. It will be taking infinite long amount of time to complete that process in order to transfer a finite amount of heat. Whereas the second process, in which externally it is irreversible, but internally it is reversible, and this process is practically possible in finite time. Okay, because if you take a pressure cooker, so in pressure cooker outside temperature is hot, wherever inside temperature, of course in the real system there will be small difference, but it can be idealized closer to a internally reversible system. So internally reversible processes are practically possible processes because these can be achieved in finite amount of time with small deviations from the actual practical conditions. Is this one clear? So now you can understand this actually. So right now you can see that I was having any cycle which was receiving heat from T1 temperature, Q1 amount of heat, doing W net amount of work and rejecting Q2 amount of heat to another thermal reservoir which is at temperature T2. Normally for a heat engine, the heat rejection is done to the environment. Okay. So if I have to transfer heat to environment in finite amount of time, what should happen? The portion of the heat engine which is transferring heat to ambient, that should be maintained at slightly higher temperature than the surrounding. Then only that process will be possible in finite amount of time. Is this point clear? Clear or not? For example, your IC engine, internal combustion engine, it is nothing but a heat engine. Okay, so in a car engine we have a radiator, and what radiator does, behind the radiator there is a fan. That fan takes the air from ambient and then it cools down the coolant with it flowing through the tubes of the radiator. So typically the temperature of coolant is 80 to 90 degrees Celsius, whereas ambient temperature is 25 to ambient air temperature is 25 to 30 degrees Celsius. So it means that the working fluid of the heat engine, if the process has to be done in finite amount of time, has to be at slightly higher temperature than the ambient temperature. Is this point clear? So it means if this heat engine has to be operated in an finite amount of time, then T2 has to be greater than equal to TA. Okay, so if T2 is greater than TA, then the process cannot be externally reversible. But there can be some scenario where the process is internally reversible. For example, in your power cycle, Rankine cycle, do you know what happens in heat rejection process? Heat rejection process, inside the condenser, saturated vapor enters and it gets converted to saturated water. All of you, have you forgotten about Rankine cycle? If you recall, then in the Rankine cycle, you might have studied this type of diagram, TS diagram, where there is this process, okay, 4 to 1. In this process 4 to 1, what happens? Saturated vapor is converting into saturated. Okay, so internally phase change is taking place upon removing the heat, so it can take place at constant temperature. So it means the process will be internally reversible. If my, say, the other working fluid to which it is removing heat, it is at some lower temperature. Is this one clear? All are clear with this idea? So it means that if T2 is greater than TA, then it is possible for internally reversible process. Okay, so it will be possible for internally reversible cycle, heat engine cycle. Okay, but if you have to take that totally reversible heat engine cycle, then the process has to be externally also reversible. And for the process to be externally reversible, this T2 temperature has to be equal to temperature of the surroundings. Is this point clear? So T2 will be equal to TA for totally reversible heat engine cycle. All are clear with this point? Heat engine it is? Yes. Generally, practical heat engines are internal. Their idealization is actually internal. Okay. All are clear with this point? So totally reversible heat engine cycle, for that T2 has to be equal to TA. Now, what is the popular name of totally reversible heat engine cycle? Carnot. Okay, so this is nothing but a. Now, of course, I will be explaining in detail, but some hint you can get from here itself why Carnot cycle is not possible. Because it will be taking infinite amount of time for doing the heat transfer process. Okay. So, for a heat engine, one important condition I have got, that T2 has to be greater than equal to T. Okay, T2 has to be greater than equal to T. If it is equal to TA, it means we are talking about a totally reversible heat engine. If it is greater than TA, we are talking about internally reversible. Fine. Now, what was the other device which typically we study with second law of thermodynamics? The other device we study is refrigerator. Okay, where the task of the refrigerator is to cool a substance below the surrounding. Okay, for example, surrounding is at 40 degrees Celsius. The room or some freezer you want to maintain at 15 degrees Celsius. So what you will be doing, you have to remove the heat from 15 degrees Celsius, and ultimately back side of the refrigerator, we see the condenser of refrigerator is typically placed in the surroundings. Okay, and one more experience you can see from the practical cycle. If you see the surrounding air, you does not feel that much hot. Of course, you are feeling hot, but if you come towards the condenser coil, you will be feeling even more warm. Okay, so it means that a refrigerator, how it can operate, you can have condenser of refrigerator at some temperature Tc, and to this QC amount of heat will be rejected. Of course, that heat is coming from nothing but a refrigerator which is taking W net amount of input work, and when it is taking W net amount of input work, it is removing QE amount of heat from the space which is maintained at temperature T. Is this one clear? So this is nothing but my refrigerator. Why I am drawing these separately? Because I am trying to draw this with reference to the atmospheric temperature condition, so that you can understand what are the operating temperatures of heat engine, refrigerator and heat pump with reference to the atmospheric temperature conditions. Is this one clear? So what will be happening over here? All are clear up to this point? So here you can see TE is nothing but, this is typically the space which we need to maintain at low temperature. Okay. So of course TE will always be very small in comparison to ambient temperature. Is this one clear? And after taking heat from this space by employing W net amount of work, refrigerator is actually dumping that heat into the atmosphere. If it has to dump this heat to atmosphere in an internally reversible manner, then Tc has to be greater than T. This will be for internally reversible refrigerator. Is this one clear? However, if you take a totally reversible refrigerator, then what will be happening? Tc has to be equal to Ta for totally reversible refrigerator. Okay? And in general, the condition can be written that Tc has to be greater than equal to. Is this one clear? What is totally reversible refrigerator? Totally reversible refrigerator again is a idealization, so it can be called as Carnot refrigerator. Okay, or reversible Carnot heat engine. If you have to reverse the entire Carnot cycle, then you will be able to achieve the refrigeration. Is this point clear? Anyone is having any doubt about this? Okay. Now we talk about third variant, which typically is called as heat pump. Okay. What is the purpose of heat pump? Like the purpose of refrigerator is to maintain the space below the surrounding temperature. Purpose of heat pump is to maintain the space above the surrounding temperature. It means our purpose is heating. Okay. So if our purpose is heating, what it means? Our purpose is heating. It means we need to take heat from atmosphere and then we need to dump it to some system which is at higher temperature than atmosphere. Okay. So in this case, in the case of a heat pump, I will be having some space which is maintained at temperature Ts, and of course this Ts will be significantly larger than ambient temperature. For example, you are living in a place here during the winters. If we talk about Mandi also, so during night time at 3 or 4 am, our temperature in December or starting of January is say less than 5 degrees Celsius. But room we want to maintain at 25 degrees Celsius. So this Ts is 25, T ambient is 5 degrees Celsius. Okay. Now if I have to maintain this room at higher condition, of course I have to supply some QS amount of heat to this, and the device which is supplying this QS amount of heat to the room is known as heat pump. Of course I can use an electric heater, but generally why heat pump is preferred, why not electric heater? Slow. Why heat pump is preferred over the electric heater? It is okay, I'll explain that also. So this is QS. Now this will be receiving how much amount of course certain amount of work it will be requiring, and it has to take heat from where? Atmosphere. So if it has to take heat from atmosphere, it means its evaporator should be placed at a temperature below the atmospheric temperature. Then only it can take heat from the atmosphere. So here will be its evaporator. Okay, and then it will be QE amount of heat it will be taking from atmosphere. So when TE is less than T atmospheric, then my heat pump cycle is internally reversible heat pump. Okay, when TE is equal to TA, then I am having, so it means TE will be coming somewhere over. Okay, so then I am having totally reversible heat pump cycle. Is this one clear? All are clear with this idea? Now we have talked about three different systems which typically are of similar nature, but the task which we want to obtain from them is different. First is heat engine. It is also operating in between the two temperature limits, but from this our aim is conversion of heat into useful amount of work. We have second device which is again operating in between the two temperature limits, but here our purpose is to cool a space below the surrounding temperature. Okay, so it means we have to now reverse the flow of heat. We have to transfer heat from low temperature to high temperature. So this process cannot take place spontaneously, so we have to supply W net amount of input to the device which is doing this. Okay, and the third scenario is where our interest is to maintain our space significantly above than the atmosphere. So this device is nothing but a heat pump. Again, here we are transferring heat from low temperature to high temperature. So the nature of device will be identical to that of refrigerator, but the only difference will be coming in the temperature limits in which it is operating. Is this one clear? And here also it will take W net amount of input. All are clear with this idea? Now, okay, so first let us talk about only the heat engine cycle, then I will discuss about it. Okay, so if I talk about Carnot heat engine, what type of components I need to use if I have to operate Carnot heat engine? First point you have to understand is any heat engine can be achieved by variety of means. Okay. For example, you can take simply a piston cylinder system. In the piston cylinder system, you can follow 4 different processes which are required for Carnot heat engine. What are the 4 processes required for Carnot heat engine? Please tell me. Isothermal heat addition. What else? Reversible adiabatic or isentropic, because all reversible adiabatic processes are isentropic. Isentropic expansion. Then isothermal heat rejection. And then okay, so all these 4 processes can be achieved in variety of ways. For example, you can achieve all these processes inside a piston cylinder system. Okay, so if you achieve this inside a piston cylinder system, typically we use air as our working. Okay, now these processes can also be achieved in the 2-phase design by using a boiler, then turbine, condenser and a pump. Okay, so I will not discuss all, let me discuss only one. So first let me consider that I have a boiler. Boiler is nothing but a type of a heat exchanger. So in general sense, if I have to tell, I can simply write it as a heat exchanger. All are clear with this point? Now, inside this heat exchanger, if I say that saturated liquid is entering, what is happening? Saturated liquid is entering. All are clear with this point? And then in this heat exchanger, I have some heat source which is maintained at temperature TH. Okay, and from this TH, this working fluid of the heat exchanger will take QH amount of heat. After getting QH amount of heat, we will keep on heating this till the entire liquid gets converted into saturated. Once we have saturated vapor, then I will pass this saturated vapor through a turbine. Now in this turbine, what will happen? Isentropic expansion will take place and shaft of the turbine will rotate to produce WT amount of work. Okay, WT amount of work will be done by the turbine. Now, we all know that when expansion takes place in a turbine, what happens? Pressure decreases. Okay, because it is producing some W amount of work. So, of course, the energy of working fluid will be utilized. Okay. Let me also parallelly draw the TS diagram. So, what you are having at the entry of boiler? This was the entry of boiler. All are clear with this point? Let me call this as state 2. So this is state 2, saturated liquid. At the exit of boiler, I have state 3. Okay. And then 3 to 4 process is isentropic. On TS diagram, how isentropic process will be looking like? Like this. And so this is state 3, this is state 4. Now after point 4, what I will be doing? I will be using a condenser, and to a limiting condition, this condenser has to transfer the heat to a ambient surroundings, okay, TA, and it will be transferring, say, QC amount of heat. After transferring heat, it has to come to state 1. And now you can see the point 4 where it is. If you see constant pressure line on TH diagram, that will look something like this. So it will be some pressure pH, and I will be having some another constant pressure line PC, where PC is less than pH. Okay, so it means the pressure at the exit of condenser is less in comparison to the pressure required in the entry point of the boiler. So what I need to do, I need to increase the pressure. To increase the pressure, I will be using a pump, and this pump will be taking WP amount of work. Okay, so once it is taking WP amount of work, then I am taking actually this part. So it means that, and again 1 to 2 is a, has to be which process? Isentropic compression. So if the entropy of point 2 and point 1 has to be same, then on TS diagram 1 to 2 will be looking as a vertical line, and this cooling process must stop at point 1. Is this point clear? In this scenario, it is very important to understand that if my cycle is totally reversible, because I am talking about Carnot cycle. So Carnot cycle is a totally reversible cycle. If cycle is totally reversible, then the temperature from 2 to 3 should be equal to temperature of heat source, which is equal to TH. And bottom temperature, temperature of condenser, temperature of working fluid inside the condenser should be equal to ambient temperature if I am operating with ambient. Okay, so for, of course, for achieving highest efficiency, I will be operating with the ambient. Okay, so this is TC, which is equal to T. All are clear with this point? So this is nothing but my reversible, this is nothing but my Carnot heat engine cycle. So it means that previously whatever TS you have placed, and you have considered that Q1 amount of heat is taken inside the heat engine and it is producing W net amount of work, which will be equal to WT minus WP, because pump will be taking input, turbine will be producing output. Okay, and then it is rejecting Q2 amount of heat to ambient. Then inside this circle is basically all these three, all the four components. So this entire thing is actually forming your Carnot heat. Is this one clear? So inside the circle, all the four components need to be placed and operated in a simultaneous fashion. Anyone is having any doubt up to this point? This is not our job, okay? Because we don't want to do refrigeration. We don't want to produce work output. What we want to do? We want to do refrigeration. Okay. But still, is this Carnot cycle practically possible? No. What are the reasons why it is not practically possible? Please tell me. First is at 4 we have more amount of liquid. So typically it is not good for the health of the turbine. Okay, but still turbine can damage at the rapid rate, but if you practically want to operate, it will operate. Okay, so that is for improving the health of the turbine, one practical aspect, but still this is not the point that cycle is impossible. What makes it impossible? Please tell me. Entropy तो वो बात की बात है, that is in the practical cycle. If I have to operate everything in ideal fashion, why it is not possible? You think about this process. This process will take how much time? It means a fluid element which has entered at this point, that fluid element must take infinite amount of time to reach to this end, then only it will be converting into vapor. It will be able to get the sufficient amount of heat to convert into vapor. However, process inside the turbine has to be isentropic. What is the meaning? Isentropic means reversible adiabatic. So if this process has to be adiabatic, it means heat transfer with surrounding will be equal to 0. So if a working fluid enters at infinite pace, infinitely small pace, it will be getting sufficient time for heat transfer to take place. So if this process has to be achieved in an adiabatic fashion, if one fluid element enters at this point, it should move infinitely fast so that it do not get sufficient time to exchange heat with the surrounding. So it means that one component has requirement that working fluid should flow at infinitely small flow rate, and other component is having requirement that working fluid should enter at infinitely. So can this operate in a continuous manner? Okay, so this is the reason why actually this heat engine, Carnot heat engine cycle is not possible. And of course, other than that, there are practical reasons. One of which is point number 4, quality at point 4 is actually large, which will be deteriorating the health of the turbine. Second point is here at point 1 we have mixture. Okay, so typically for increasing the pressure of liquids we have pump, increasing the pressure of vapor or gases we have compressor. We do not have any device which can handle the mixture of liquid and vapor simultaneously during the compression process, because if we have mixture at the compression process, then we will be having cavitation and other things. Is this one clear? Okay, this is not our point of discussion. Okay, let me also now, before this, let me also try to find out the efficiency of this. So if I have to find out efficiency of this Carnot heat engine, how much it should be? What is efficiency? Efficiency is always desired output by input. What is desired output? For a heat engine, desired output is work done. Yes, net amount of work output. And to achieve that work output, what supply you are doing? You are adding heat. So in the boiler you are adding heat. So heat input is basically the input. Now W work output will be turbine work minus pump work, and heat input will be heat added in the boiler. What will be turbine work? How to calculate turbine work? Please tell me. Let us calculate it on per unit mass flow rate of the working suction hours. Okay, I will not multiply mass flow with the working. Let me calculate it on per unit mass basis, because mass here and here it will be cancelled out. How I can calculate work done from an turbine? Turbine process is 3 to 4. Okay, what is this process? It is a steady flow process. Is it steady flow process? Tell me. Isentropic turbine, if whatever working fluid is coming at the inlet, same working fluid is going at the outlet, it is nothing but an steady flow process. For steady flow process, I have to apply steady flow energy equation. What is that? Q plus H1, sorry, here it will be H3 plus V3 square by 2 plus GZ3 has to be equal to W on per unit mass basis. Let me write then small q. Small Wt work output plus H4 plus V4 square by 2 plus GZ4. All are clear with this point or not? Now I will be making assumption that changes in kinetic and potential energy are negligible. So if changes in kinetic and potential energy are negligible, these terms will be going away. The process inside the turbine is reversible adiabatic. For adiabatic process, Q will be 0. So it means W turbine will be nothing but equal to X3 minus H4. So here I can write X3 minus H4 minus of, please tell me, what will be pump work? What will be pump work? H2 minus, what will be Q in boiler? H3 minus H2. Again you have to apply steady flow energy equation over there. All are clear with this point? So this is how you can calculate the efficiency of Carnot. Okay, and of course I am not going into further details, but I can also tell that efficiency of Carnot heat engine can also be written as 1 minus Tc by, okay, I am not actually deriving that. Okay, so we also know that efficiency of Carnot heat engine is 1 minus Tc by. How that will be coming? That is also very easy. From here only it will come. You can write from first law of thermodynamics. What is this? This is a thermodynamic cyclic process. From first law of thermodynamics, can I write cyclic integral of del Q equal to cyclic integral of del W? Then cyclic integral of del Q will be Q in minus Q out. This will be WT minus WP, which is W net. So W net can be replaced with Q in minus Q out. So what will be efficiency then? Q in minus Q out, Q in 1 minus Q out by, okay. Now go to this 4-to-1 process. We also know that for a reversible process, what is 4-to-1 process? It's a reversible process. For a reversible process, heat can be given as integral of TdS. Okay, so you can see for 4-to-1 temperature is constant, which is equal to Tc, and integral of ds will become S4 minus S1. Okay, so this is my Q out. Similarly, Q in will become equal to Tx into S3 minus S2. I am writing small s because I am using the per unit mass. Okay, I am not making mass. Okay, so now because entropy of point 3 is equal to entropy of point 4, entropy of point 1 equal to entropy of point 2. So S1 is equal to S2. It can be written as, so this entropy will be cancelling out. Okay, and finally what I will be getting? 1 minus Tc by, fine. Entropy from where it is cancelling? S1 equal to S2 and S3 equal to S4. Substitute this, you will be cancelling it. Okay. Okay, this is not our discussion. Probably today we took good amount of time in discussing thermodynamics. Now, what we need to do? We need to operate a refrigerator. If I have to operate a refrigerator, what I need to do? I need to reverse. See what is happening. You see in this block diagram. In this block diagram, I am taking heat from high temperature and I am rejecting heat at low temperature. Now what I need to do? I need to take heat from low temperature. I need to reject heat at high temperature. Similarly, here I was getting work output. Now here I have to give Work input. Here I was getting work, I was giving work input, here I will be getting work out. Understood? So all these things I have to reverse. So what I do now, I will take a heat exchanger and what is this cycle? Reverse Carnot cycle. Okay. At reverse Carnot cycle, I can also name it as Carnot refrigeration cycle. All are clear? So this is a heat exchanger. Now in this heat exchanger, substance will be coming at mixture state. Okay, it will be mixture of, because I need to follow the entire TS diagram, just I need to reverse the path. So I will be coming at state 1, mixture state. So at the mixture state I am coming over here, then what will happen? I must have something which can, what I need to do now, please, if I have to reverse this cycle, what I need to do? I need to move from 1 to 4. I need to move from point 1 to point 4. So if I have to move from 1 to 4, I have come from 4 to 1 after removing the heat. So if I have to go from 1 to 4, I have to add heat. Okay. So it means below this I have to take some space which is actually adding heat to this. Once it is, say it is adding QE amount of heat, then I am coming to point, let us keep the same point, 4. Then from 4, now I have to go to point 3. So it means 4 to 3 pressure is increasing. So if I have to increase the pressure, I have to use a compressor, because compressor or pump, basically compressor, because I am having more amount of vapor. Okay. So then I will be using isentropic compressor. Now you see the symbol. In expansion process, entry point is narrow, exit is widening. Here entry is wide and exit is narrow. Okay. So 4 to 3. After this, from when I have come from 2 to 3, I have added heat. Now I have to go from 3 to 2. What I need to do? Remove the heat. Okay. So again I will be using some heat exchanger, and this, from this heat exchanger I have to remove the heat. So QC amount of heat I have. Okay. Then after this I have come to state 2. Now from 2 to 1 I have to decrease the pressure in an which manner? Isentropic manner. So if I have to decrease the pressure in isentropic manner, I have to use a turbine over here. Okay. So now I will be using a turbine which will be giving me state. All are clear with this? So now the cycle is completely reversed and I have transferred heat from, okay, what is happening here now? I have mixture of liquid plus vapor initially which is having low quality, and now its quality is actually increasing. So it means that evaporation of liquid to vapor is taking place. So, sorry? Yes, practical mein mujhe pata hai. All are clear with this point? So, what I need to do here, please tell me. Here, liquid plus vapor mixture is changing from low quality to high quality. It means that here, what is happening? Liquid is converting into vapor. Evaporation process is taking place. So, we call this heat exchanger as nothing but evaporator. This we call as, so it is taking WC amount of work, we call this as, this is turbine, again producing WT amount of work, and The heat exchanger where vapor is converting into liquid is something which is called as condenser. Okay, so I am having now, earlier I was having boiler at the top and below I was having condenser. Now evaporator is at the bottom and top I have condenser, and pump or turbine are swapped. Okay, so again I am having the same TS diagram, but processes are taking place in reversible. What is process 1 to 4? Isothermal heat addition. So earlier the process which was heat rejection, it has become heat addition. It is process, what is 4 to 3? Isentropic compression. 3 to 2 isothermal heat rejection, and 2 to 1 is isentropic. All of you try to find out its coefficient of performance. What is COP? What is COP of a refrigerator? Desired output upon input. What is desired output? To produce the refrigerating effect. Okay, so for producing refrigerating effect, I have to transfer QE amount of heat in the evaporator. And to do this, what input it is taking? Work. So WC is the compressor work, input work, minus WT is the turbine. So this will be COP. Try to expand this the way I have explained for the case of a heat engine, and in the next class tell me what will be the final formula for COP of a Carnot refrigerator, and you have to also tell me what are the limitations why it is not practically possible. Okay, and also please revisit your concepts of thermodynamics.